Hi, Tony. How are you?
Good. What about you?
Yeah, I'm doing well. Were you able to solve the problem, the projectile one? It's I think which one?
Yeah, actually.
Okay. Were you able to solve the? We will start in a few seconds. Okay. So, do you have any other questions on like homework 2, homework 3?
Not that I know of yet. I'll send you an email if anything comes up, though.
Sounds good. Right. Does anybody have any question? I have two of you here. Okay. Just like I would like to check that everything's okay, and from this week we'll be having a help session, I think, on Wednesday based on the survey that I sent to you guys, and I think we will be having the help sessions. It's like an office hours. It will be on Wednesdays, and the quizzes will be on Fridays. I have only 11 votes, and we have like 22 students in this class, so we still have like another 11 votes missing. So if somebody wants have preferences for the help session time or the quiz time, it will be good. Like you fill the survey, so we can weigh in your votes in the decision. All right. So last time we have been talking about curvilinear motion, and we used polar coordinate systems, and the two equations that we have from our last time. So let's put the equations that we have. So we got the velocity vector is equal to r dot in the direction of the ur hat plus r theta dot in the direction of u theta hat. So this is for the velocity vector, and if you differentiate this with respect to time, it should give you the r double dot minus r theta dot square in the direction of the ur hat plus r theta double dot plus 2 r dot theta dot in the direction of the u theta hat. So you are not required to memorize these equations. It's in the dynamics sheet. So what you have to do goes to the dynamic sheet and pick the cylindrical coordinate system and use this equation from. If you want to memorize it, it's it's your decision. So let's see how we can directly apply these equations to a problem. So let's solve this example. So basically in this example, let's solve this part one. It says that you have like a ring that has an oval shape, and there is a rod that moves on the constraint to the ring at C. And this constraint is a double collar, so it's pinned and allows the collars, one of them on the rod and the other on the ring. So the so the rod is restrained to move on the ring. So we have R here, so R measured from the origin here up to there. And the R's keep it changing as the theta is getting increased or decreased. And this is how the R is changing. So it gives you the R, and also it's given the theta dot. So it requires you to determine the radial and transverse components of the velocity and acceleration at t equal 1 second. So let's list what we have. So we have here theta dot, which is equal to e to the power 0.5 t square. So we can get, because it's required to get the acceleration at t equal 1 second, so you will have to substitute with t equal 1 second in theta dot, so you can get e to the power 0.5, and when you calculate this, it will give you 1.65 radian per second. It's very easy to get theta double dot by differentiating this. So if you want to differentiate this, so you will differentiate the power term, so it will be e to the power 0.5 t squared multiplied by the derivative of this term, which is t. And if you want to calculate theta double dot at t equal 1 second, so it will give you e to the power 0.5 multiplied by 1. Sorry, 1. So it should be 1.65 radian per second. If you want, so this, we got it by differentiating d dt, and if we want to get theta, so we will have to integrate this. So we'll have to do integration with respect to the time. So e to the power 0.5 t squared dt. And we need to use the integration upper and lower bound. So the upper bound is 0, theta at 0, and sorry, we are differentiating with time. So we have dt here. So t equals 0 up to t equal 1 second. You can easily calculate this using calculator. Don't attempt to do this because I mean, like, do it from very simple principle by doing a general integration, because it's a very complex integration here. So you basically use the integration function in your calculator, and will give you 1.195 radian per second. So we got theta, theta dot, and theta double dot. Let's do the same with r. So we have r is equal to here 0.4 sine theta plus 0.2. So r dot, when we differentiate, this one will be 0. So this is the only term that we will need to differentiate. It will be 0.4 cosine theta multiplied by the derivative of theta with respect to time, because we are differentiating with respect to theta, with respect to time, not to theta. So if it's theta, it will be 1, and here will be 1. But we are differentiating with respect to time, so it will be theta dot. And we need to calculate r at 1. Okay, I think we, so we need to calculate, yeah, we have the theta. So this is theta at 1 second, theta at t equal 1 second. It will be equal to 1.195 radian. So we need to calculate theta with degrees. So if you calculate this with degrees, it will 1.195 multiplied by 180 over pi. It should give you theta equal to 86.47. I calculate theta in degrees because I needed to get r at this theta, at theta equal, because this is the value of theta at time equal 1 second. 0.47 should be equal to, when you substitute, so let's make it here. So this one will be, let's put it here. So it will be 0.4 sine 86.47 plus 0.2. When you calculate this term, it should give you 0.572, and r should be in meter because all our dimension is in meter. And then we will come back to the r dot as we did it from before. It will be 0.4 cosine theta multiplied by theta dot. So we know, let's get r dot at theta equal 86 0.47. So it should be equal to 0.4 cosine 86.47 multiplied by theta dot, which is here, 1.65 radian. And when you do this, it will give you 0.292, and R should be equal to meter per second. And the second thing is the R double dot. So we need to differentiate this one more time. So give you negative 0.4 sine theta multiplied by the derivative of this, which will give you theta dot. And we have another theta dot here. So it will be squared plus the derivative of the second term multiplied by the first term. So it will be 0.4 cosine theta multiplied by theta double dot. So this is how the term look like. And when you substitute with theta and theta dot and theta double dot with these values, so here's theta, and here's theta double dot, and here's theta dot. So we have all these values. You will be able to get R double dot at theta equal. So it should give you negative 0.77 meter per second square. So we got all the values needed, R, R dot, R double dot, and similar theta that is needed to calculate these terms. So what we will basically do, we will take this equation and do direct substitution to get the polar and tangential, the polar and the polar coordinates, like the velocity in terms of polar coordinates. So let's see if we can copy this. All right, so if we want to get V, so the V vector will be equal to R dot 0.292 in the direction of the UR hat plus R, which is 0.572 multiplied by theta dot, which is 1.65 in the direction of the U theta hat. So when you get the final answer, so it will be 0.292 in the direction of the UR hat. And when you do this multiplication, it should give you 0.944 U theta hat. And the acceleration, you will have R double dot negative 0.77 minus R, which is 0.572 multiplied by theta dot square. So theta dot square 1.65 square. All of these are in the direction of the U R hat plus R multiplied by theta double dot. So we have R 0.572 multiplied by theta double dot. So we have 1.65 plus 2 R dot 0.292 multiplied by theta dot, which is 1.65. And all of these are in the direction of the U theta hat. So when you calculate this, it should give you negative 2.33 in the direction of the UR hat plus 1.74 in the direction of the U theta hat. So basically, it's just like most of the work is in the integration and differentiation to get the theta, theta double dot, and theta dot, and similarly R, R dot, and then it's direct substitution in this equations. So this is most everything about the coordinates that we will be dealing with in the dynamics, including Cartesian, tangent normal, and polar coordinate system. And I have an example from Dr. Dan Baker that can show you what is the difference between these coordinate system. So if we have this vector A here, and this vector A starts from point on this curve up to tip, this tip could be anywhere. So let's have it here. If we are talking about if we want to do vector algebra using Cartesian coordinate system, so this is how our axes will be look like. It's usually in the x and y direction. It could be positive and or negative, depends on the direction of the vector. So if I make it like this, so the x will be 0 and the y will be 0 and all the magnitude will be in x direction. If I have it like this, I will have the y is getting increased and the x is getting decreased. So this is how the vector look like in terms of Cartesian coordinate system and how's the direction look like. And it will be positive or negative depends on your direction. So we know that these are the positive direction of the vectors. But if I make it like this, so x will be negative and y is still positive. And if I make it like this, x will be negative and y will be negative. And if it's in this quarter, it will give you x positive and y negative. So this is for the Cartesian coordinate system. So if we remove the Cartesian and look at the tangent normal, so the tangent is always tangent to the curve, as you can see here. It's always tangent, whatever your vector look like. And the normal is always in the direction of the radius of the curvature. So so if I move this point, you will see it's the direction will be is always to in the radius of the curvature, like the center of curvature, where it is, it might be here. So it's in this direction. And this is how is the vector look like. If my particle shoot on a straight line, so most of the velocity will be in the tangential and there will be zero normal. And here, if my vectors look like this, so it will be like we will have a normal direction. So this is for the tangent. If we are looking into a cylindrical coordinate system, so the cylindrical coordinate system, as you know, we have a center of motion, and we have a line moving from the center up to the particle, and the r direction is always in the direction of the r, and the theta is perpendicular to the r in the direction of the increasing theta. So something like this. So this is how it shows. I might put it on Canvas page so you can play with it and understand the difference between if you solve any problem with any of these coordinate system like Cartesian, tangent, or cylindrical, it should give you the same answer. Just like there are different ways to solve the problem and make it easier. Sometimes it's easier to do a tangent normal. Sometimes it's more easier to do a polar coordinate system. Depends on what's given to you in the problem. And I might like upload a sheet that shows you where's the best to use each one of these coordinate system. Depends on the what's given in your problem. So what about now if we try to do a class exercise to see how you understand the different coordinate systems. So how many we have here? We have 8 of you. We might like divide you into 2 breakout rooms, and I will put a link for an exercise here. So this exercise, it shows you that there is like a teacup. A teacup is moving on this path, starting from here. Like imagine that you are playing with this teacup thing, and you are here, and this is teacup. How about if we put it on the All right. Yep. Okay. So it starts from here, this teacup like this, and move on this flower bath. And here's how is the R is changing. So the R like starts at this location and keep changing. And also this is the direction of the increasing theta. So you will be asked some question to construct the polar coordinate system and also the tangent normal coordinate system. And based on the givens in this problems, it tells you that the uh, uh, this teacup will move in a flower path and be guided by a extending arm R, which rotate around origin O. Use the information provided in the diagram, and that the velocity at this location is getting smaller. So we know that the velocity is getting decreased, which will give you some insight about the acceleration. So here's the velocity vector, and I need you to draw the tangent normal and the polar coordinate system at this point, and then answer these questions. What happens to the velocity? Is it in positive or negative direction? And what about the tangential and normal acceleration, and also the radial and transverse velocity, and also the angular velocity? So we need to know the answer of all of these questions. So I will assign you guys to a breakout room. To think about it for like 4 or 5 minutes. So let's make 2 breakout rooms. Okay. Looks like there is still some discussion in room 1.
Recording.
All right, so let's see how we can do it. All right, so for this teacup, it gives you the V tangential at the V, and we know that the V is always in the tangential direction. So this will be our tangent direction, and the normal direction is perpendicular to the tangent and in the direction of the center of curvature. So this is how it looks like. And if we want to draw the polar coordinate system, so we know that the r vector is in the direction of r, so we know that this is r, so here's how r look like. And for the theta is perpendicular to the r direction and in the direction of increasing theta. So we know that theta is increasing in this direction, so here's how theta look like. So this is the first part of the problem. Yeah, for the second part, which it needs the direction of the velocity. So is it positive or negative? So the velocity is always positive in the direction of the tangential, so it's positive. And for the tangential acceleration, so let's see how the acceleration directions look like. So we know that the V is slowing down, so the tangential is in opposite direction. If it's increasing, so it will be in the same direction of the velocity. And the tangential acceleration is always, the normal acceleration is always in the direction of n. So in this direction. So we know the tangential acceleration is negative and the normal acceleration is positive. So for the radial velocity, so let's see how the radial velocity look like. So this is r and this is theta, and this is the extension of theta. So if you analyze this v into r and theta, so you will find that the vr should be in the r direction. So let's pick this pen. Should be in this direction, and the theta, v theta, will be in this direction because the v vector is in between the positive r and the negative theta. So here's how vr look like, and this is how v theta will be look like. So based on this, you will find that the radial velocity is positive, and the transverse velocity v theta is negative. because it's in the negative direction of theta. So let's get to the angular velocity theta dot. So based here's the v theta direction. That means that the theta dot is in this direction, because if you go back here and found the v theta, it's r multiplied by theta dot. So r is always positive, but theta dot will be taking the sign of the v theta, and we know that v theta is negative, so theta dot is negative as well. So that means this is how the v theta dot look like. So it will be negative as well. So this is how you should think about the problem. You might be given this problem in one of the quizzes. It was numbers, and you will have to calculate this number after giving, like, for example, the tangential and the tangential velocity and the tangential acceleration. You will be asked to get the normal acceleration. So you should be able to construct the normal and tangential axes. So this is for this example, and with this, we are done with all the coordinate system, and we will just like have a couple of applications on this thing, which is one of them is chapter 12.9, the dependent motion, and we will have the chapter 12.10, which is the relative velocity. So let's see what about dependent motion analysis. So for dependent motion analysis, we are mainly talking about pulleys. Like, you have a fixed surface like this, and you'll have a pulley here, and there's a rope moving. Oh, sorry. A rope like this, and let's have our second big pulley like this, and then this is attached to the roof here, and we have some kind of weight at this location. So for these problems, you will have like this is a pulley. These two pulleys is fixed to the roof here, and you have this one is moving, and let's call this A, and you have some kind of weight at this location, and let's call it B. And you are like given the velocity of one of them, and you will be asked for the other velocities. So let's see how can we tackle these problems. So for these problems, we know that the length of the rope is not changing. So this rope or this wire is not changing from here up to here. So if we were able to calculate the length of this rope and differentiate it with respect to the time, we will be able to get the velocity of A and B. So, like, for example, if we know that the B is moving down, so what will happen, this rope will pull down, and it will move this direction, and this will move in this direction, and this will move in this direction, and this A will go up. So as soon as you pull B, A will go upward. If you let B go upward, A will go down. So we need to know these velocities, A and B. So first thing is that, which is the hardest part, you can say that the length of the rope will be equal to this part. And let's make it like this part, and let's say it's L1. And then you know the half circumference of the circle, and let's call it S1. And then you will have from here to here, let's call it L2, and you will have to calculate this distance, and then you get this distance, and this one, and this one. And you will be having an equation with some like L1 plus S1 plus L2 plus S2 plus L3. So it will be very, very long equation. And then you will differentiate this with respect to the time. So you will say that dL dt will be equal. But you will have here some constant lenses, like you know that the rob here at this location is not a changing. So the ds1 dt will be equal to 0. And you know that this distance is not a changing. So the derivative of this with respect to the time, and this one is not a changing because this is fixed and this is fixed. So this length will not be changed. So it will be, the derivative of this length will be 0 and this will be 0. But this length is a changing because this is going down or going up. So this length L4 is a changing. And this length is a changing because I know that this pulley is going up. So this part of the length is keep changing. But I know that this part at here is not a changing. Only this part is a changing. So the most efficient way to solve these problems is to identify the variable lengths. So let's see how can we identify the variable lengths for this problem. So let's draw it one more time. And we have a pulley here and a pulley at this location, and they are fixed here. And we have another big one here. And let's have these two should be at the same level. They are fixed here, and we have our weight here. So to solve these problems, you will have to identify a fixed axis like this one. You know that these points is not a changing. So this is our fixed axis. And then identify the variable lengths. So what are the variable lengths in this problem? So you know that this length from here to here is variable, and similar is this one because I know that this pulley might go up and down, which will change these two lengths. And also this one will changing from here up to here, depends on the location of these. So this are the variable lengths, and let's call them like this one will be SA, and this is the direction measured from the fixed axis, and this we will call it SB. And rather than getting the length of the rod, we will get the like you know that the length of, let's get the length of the rod. So the length of the rod will be this variable length, and we have two of them. So it will be 2 SA, and we have another variable length, which is SB. And the other lengths, including this part and this part, the part that is around here, and all this part, all these, we will call them constant. And this will be equal to the length of the rod. So this is how we get the length of the rod without getting into too much detail. How long is this and how long is this and that, because all of these will be constant and not a changing. The only changing is the SA and SB. And then you might like want, and you know that the length of the rod is constant as well. So the length of the rod will not change, and we have a constant here. So you can finally say that 2SA plus SB will equal to L minus C, and we can call this C1, another constant. Then you can differentiate this with respect to time. So you will have 2 multiplied by the derivative of SA, the time rate of a change of the length of this part with time, which will be VA, plus the time derivative of SB, which will be VB. And if you differentiate the constant, it will give you 0. So this is how it works. You identify a datum, and you see what are the variable lengths, and then put them equal to constant, because you know that the variable lengths plus constant lengths on this rod will be equal to the length of the rod. And you know that both lengths of the rod and this constant will give you another constant then you differentiate them with respect to the time. It will give you the relationship between the velocities at A and B. So if we know that the VB is moving downward with 1 meter per second, so you can get VA will be equal negative VB over 2, so it will be negative half meter per second square. So it will go up 0.5 meter per second. Oh, sorry, meter per second, not square. It's the velocity. So here, and this is rational because as you know, if B is going down, this drop will be pulled down and this bully will go up like this. So this is how it works. Let's see some like examples that shows how this bully thing works. Like for this example, as you can see, if we want to determine like, let's get this copied. All right. Okay, so let's identify what are the constant lengths in this problem and what are the variable lengths. So as I told you, you will identify a datum and then you will measure what are the variable locations. So you know that this pulley is free at this location. It's free. And you know this pulley is fixed at this roof, so it's not free. And you know that this body A can move, like goes like this or like this, depends on how's the motion look like. So what are the constant lengths? So if you take this datum, you know that this red area is constant and this part is constant and this part is constant. So all of these are constant. So you will have SP is variable and you have two of them. You have another, you have a one here and a one there. And you know that this part is variable. So you know that SA is variable as well. If the body A is moving backward or forward, so the SA will be changed. How about H? Does anybody know if H is a variable or is a constant in the rope lengths? Anybody can answer.
Wouldn't that one be constant?
Exactly. Why?
Because it's between the pulley that's locked in place on the roof and the pulley that's locked in place on the ground.
Exactly. Yeah, because we have a fixed axis. This pulley is locked and this one is locked as well. So when you differentiate, if you put the equation and differentiate, so H will be 0 because it is not a changing. It's because it's in between two locked pulley. So you might put in the equation and when you differentiate, put it 0, or you don't have to put it in the equation and you finally, your equation will be end up with 2 SP plus an SA. So this are the variable lengths plus some constants. These constants include this red lines, and you might put H, and all of these will be equal to L. And you know that all of these are equal to constant. The length of the rope, the H and the C, so all of these will be equal to constants. Or from verse, you say that 2SP plus SA is equal to constant. Whatever it's best for you, you can do it. And then finally, 2VB, when you differentiate with respect to time, plus VA will be equal to 0. So this how the relationship between the velocities will be look like. And if you take another derivative with time, and it's given the acceleration, so 2AB plus AA will be equal to 0. So let's solve a problem here. Like, how about if we Okay, so let's pick this one, 2 row. Okay, so this is a multiple row problem, and you have all these fixed pulleys, and this row number 1 in brown and row number 2 in blue, and you are given the velocity at B. So just make sure how many bodies are free. We have the weight at B, and also pulley E is free and pulley D is free. So we have 3 particles are moving free. And you have B, but B is constrained by D. So the velocity of D should be equal to B because this is a fixed between here and here. So if D is going up, B will go up with the same velocity. So let's see how can we solve this problem if we have multiple ROP. So for multiple ROP, so let's see ROP 1, which is in brown. This is the fixed axis for this ROP. And you will have, this is the length, all these lenses are variable because E is moving. So you know that this SE is changing, and also B is moving up and down. So let's call this SA or SB. So let's put the equation. So if you put the equation, you will have SB plus, so this part, and then you will have SE, this is a 1, 2, and 3, plus 3 SEs will be equal to constant. This is ROP 1 because all these parts are constant. So this is equation 1, and let's have our equation 2. So for equation 2, we will get it from the second ROP here. So let's identify a fixed axis. So this is our fixed axis, and we know that this pulley is moving, so this will be SD, and we know that this pulley is moving, but we have SE as well, so let's move SE from here. Yeah, we already have it from here, and so this will be equal to the DSE. So let's construct the equation. I think we should have this at the same point here, like this pulley should be at the same point with this. Okay, so let's solve this problem. So you will have, this is 1 and 2, or I think we can solve it somehow. Y3 minus 2y, okay, 2 SD plus, so SD minus SE. But this should require you to have this pulley at the same point with the other one, like this should be with this one. So this is an error with the problem. So we should move this up at this location because this will add another variable to our problem. So if we like assume that this pulley at here at this location, and you will have this, I got this 2 lenses, which is 2 SD here, the length of this one, and the length of this one, and the length of the third one will be equal to SD minus SE. So solving this problem will give you that the VB plus 3 V of pulley E will be equal to 0, and this will give you 3 SD minus SE equal to constant, and finally you will have 3 VD minus, after you take the time derivative, minus VE will be equal to 0. I have VB, it's 1 meter per second, and it's going up, not down. I measure the VB down, so this will be negative. So let's get VE based on this equation. So this is the equations that I will be using. So VE will be negative 3V, oh, VE will be negative VB over 3. And I have VB is equal to negative 1 meter per second because it's going up. So it will be 1 over 3 meter per second. And if I want to get the VD, which is equal to the VB, so VD based on this equation will equal VE over 3. So it will be 1/3 over 3 gives you 1 over 9 meter per second. So this is because VB is equal to VD meter per second. So this is how I solve the problem, just like small error here. This should be at this location so we can measure from the same fixed axes. I will solve another quick problem on the pulley, and let's see, this have 1 rod, so let's solve another one with 2 rod like this, which I think this is the right problem because it's from Hippler. Here it is. So here it says determine the speed of block B if the end of the cord at A is pulled down with a speed 2 meters per second. So let's see what are variables here. We know that there is a fixed location here, and also we know that this point is fixed, is not moving, so we can have a datum at this location. And let's just see what are the variables. So we know that this pulley might go up and down because it's a free and tied to this rod. And also we know that point A could go up and down based on how you pull it downward or upward. And also we know that pulley E, which is attached to the weight P, so we know that VE will be equal to VB because both of them are attached together, and also is a variable. And we have 2 ROP. The first one is this one, and the second one is this one. So we need to construct 2 equations, one for each ROP, because we know that each one is constant. So let's solve the first ROP, and let's have this one. Okay, so we know that the variable lengths are SP, this is a 1, and we have this length. So the value of this length will be SP minus SC, because we know if we subtract these 2, will give you the length of this part. So the first one, let's have an example here. Right, so we will have SP plus SP minus SC will be equal to constant. So this equation 1, and the second equation, which is ROP2, which is this one, which will be equal to this ROP, which will be equal to this length. All right, so it should be, okay, let's see how can we get it. So this part. Oh, it should be up to this point, not this point. So we can say the first part is this part is a changing, and the second part is this entire part is a changing. So we need to get this too. So it will be S SB plus YB minus YC. So let's have this one. Yeah, so I think let's clear it a little bit. So if we want to get this part, I think all the things that I'm writing is confusing me. All right, so if we want to get this part, we need to have this part verse. So it will be SP minus SC. So it should be this part, SP minus SC, and we will have SA minus SC, which will be, oh, SP. All right, so this is confusing. So how about if we like SP? I got the first one right, so the most one will be SP. I don't know if we need, I think we can calculate this SP. And the second thing, so I got this right. So I need to get this right. I might like try to solve it with, and also you can try with me. And we need to identify the right lenses. I think it's a little bit confusing. We need like to subtract, do a lot of subtraction here to get the other lenses. And yeah, I think it's 10:45 here, so I might like think about it, and we will solve it in the early in the first 5 minutes in the next lecture. All right, does anybody have any question in the last minute? So see you guys tomorrow. Actually, I will be assigning homework for today, and it will be due to Wednesday. So you will have 2 days from now, just like 2 or 3 problems on the polar coordinate system. All right, see you guys tomorrow.
Tia, is that going to be due at 10 o'clock on Wednesday like the other ones?
Yeah.
Awesome. Thank you.
Okay, thanks.